I'm Rainer, and this week we're going to be doing a problem in which a block of mass small m, it starts moving with a speed v1, and it moves a distance d across a frictionful surface until it reaches a block of mass m, mass big M. And together, we're told, they stick together and they move off to the right, and they start compressing the spring a distance delta x uh, of spring constant k. And we don't actually know delta x, so that's what we're looking to find, given the rest of this information. So let's talk about how to solve this. We might originally think, hey, we've got a block coming in at a speed, we've got a spring getting compressed. It sounds a lot like we should use work and energy. And that's true, but there's only one little problem with just throwing this into the work energy theorem. And that is that when these two things collide, they stick together. And so we know that this is a perfectly inelastic collision. And I know that for perfectly inelastic collisions, kinetic energy is not conserved. And so in that case, the energy goes somewhere else, and I don't know quite where it goes. So I'm not comfortable using the work energy theorem because I don't know what the term describing this energy released in the collision, I don't know what it is. So instead, we can say, let's use the work energy theorem before they collide. Then let's use it after they collide. And for the middle, we know that energy is not conserved. We know that in inelastic or perfectly inelastic collisions, momentum is still conserved. So we'll use that as our stepping point. So let's go ahead and start with the first section. So I'm going to just choose as a general rule my system to be everything for all of the parts of this problem. Now, for the first interval we're looking at, which is starting with this block moving to the right and ending with these two blocks colliding, I know that I've got a change in delta k translational. I know work equals 0, and I know that there's delta k translational because I know that this slows down. I also know that there's friction, kinetic friction, and this leads to a delta E thermal term. So for delta kt, I know that's 1/2 m1, because that's the only one that's really doing anything right now. And I know it's v final, I'll call v2. Keep in mind, this is the speed of block 1 when it hits this block, squared, minus the initial speed, v1 squared. And then I know that delta E thermal is always just going to be the integral of the friction force with respect to distance. And I know that I'm going to end up with plus mu k m1g times d, distance traveled. So at this point, I can solve this for v2, and I've got a new speed. Now, what I can do at this point is say momentum is conserved for region 2. I can say P initial of the system equals P final, and my system is still everything, which in this case is really just the same as block 1 and block 2. So P initial is going to be the mass of the first one because it's coming in at a speed v2. Keep in mind, this is the speed at the beginning of the collision. P final is going to be the two moving together, m plus big M. Now I've been calling this M1, I'll keep calling it M1. Plus big M, moving at a speed I'll call V3. So at this point, we can now solve for V3, also in terms of stuff that we know. And at this final time, we can say, all right, now we've got a big block system moving at speed V3 into this spring, and so we can just go back to the work energy theorem like we always have. And one thing I'll note is we're going to ignore the remaining delta E thermal from, I know technically the small m is still on the friction, but we're going to say it moves a small distance, so we'll neglect that. So we're going to say, in this case, work is 0, my system is still everything, and I know that I'm going to have a delta k translational, this thing's going to stop, And I know I'm also going to have a change in spring potential energy. Now, in that case, I'm going to have 1/2 total M, so 1/2 little m1 plus big M times V final squared, which is 0, so I won't even write it down, minus the initial squared, which in this case is V3. I'm going to put a minus V3 squared here. And then I know that the delta U spring is always just equal to 1/2 K times the change in distance squared and stretch length squared. And I know that my initial stretch length was 0, so I'm just going to go ahead and write this down as a plus 1/2 K delta X squared. Now at this point, we've got everything in terms of stuff that we know, assuming we solve for V3 in terms of stuff that you know. And you can simply solve for delta X at this point to find compression distance. So that's all we have to do.